And it looks like we are live. Alrighty. Just do that. Oh, that was weird. Alright. Let's get some things set up. Because today we're going to be looking at solving equations that are radical or rational or quadratic in nature. So I'm going to just do this. Yeah, I think, actually, you know what? Let me just take a moment and go back to some of the stuff that we were doing yesterday. So yesterday we were looking at solving equations that were quadratic. So let's just pick back up there. Let's see, you know what this looks like? Yeah. Let's look at this one. X squared minus 14x minus 11 equals 0. So when we were talking about solving quadratic equations yesterday, we talked about this progression that we want to go through every time that we are trying to solve a quadratic equation. The first thing that we try to use is the square root property. Now, in order for us to use that, we can only have x in one term, and it has to be a square. Okay. So we don't have that. So this is not a square root property problem. The second thing that we try to do is see if we can use the zero factor theorem. Can we factor this polynomial? Well, we have a lead coefficient of 1, so we should be able to just look at this constant and see if we can find factors of the constant that will subtract to give us 14. But there's no way that's going to work. So factoring is going to be off the table. The third thing that we were trying to do is to see if we can complete the square. For completing the square, we want a couple of things very particular to happen in our equation. One is that we need a lead coefficient of 1. So if we have that, great. And we also want to make sure that our middle coefficient is even, because part of the process for completing the square is to do half of that middle coefficient and then square it. And the kind of numbers that you want to take half of are going to be even numbers. Now, you can take half of really anything, even if it's an odd number or even if it's a fraction, but it will create more problems for us in the long run. So we typically don't want to use completing the square when that's the situation. So we have everything set up here that's going to work out nicely for us so that completing the square is the best method. So the first thing that we do is that we move the 11 to the other side, so it becomes a plus 11. Now leave the gap there because we know that part of this process is figuring out what number we're going to add here in the gap so that everything on the left side will factor as the square of a binomial. So it's a two-step process, but we kind of do it all at the same time. We take half of this middle coefficient, and that's what goes in the factorization. So half of negative 14 is negative 7. And then we square that guy, and that's what goes in the gap. So we add 49. So by having that plus 49, we create a trinomial on the left side that's going to be the exact same two factors, x minus 7 times x minus 7, which gives us the square. But if I add 49, that changes the problem, unless I also add 49 to the other side of the equation. So let me add 49 over here. So now our equation is balanced. What we did on one side, we did to the other side. Now, on the left side, we did that so that we could factor. On the right side, it was for balance, and now we just add these guys, so we end up with 60. The main idea behind completing the square is to turn our quadratic equation into something that can be solved by using the square root property. And that's what I'm going to do now. I just have x in this one spot. It's contained inside of a square. So we take the square root of both sides. Now, remember that when we are the ones who are inserting the square root by using the square root property, we've got to have the plus or minus. All right, so on the left side, it's just x minus 7. That's great. On the right side, it's plus or minus, and now we've got 60. And we want to see how we can break that guy down. so that we can have, hopefully there's a perfect square that's a factor of 60. Now, if you know it, great. If you don't know it, then I suggest that you go over here to the side and you take the number 60 and you do a factor tree. Now, I think it's in your best interest to start with your smallest prime number and exhaust that before you go on to the next one. So, for example, the smallest prime number is 2. 2 goes into 60 30 times. I'm going to keep using 2 until I can't anymore. 2 goes into 30 15 times, and now I can't use 2 anymore. Looking at 15, we're going to go to the next prime number that we have, which is 3. And 3 goes in here 5 times. Now, what we see here, you've got 2 times 2 times 3 times 5. That forms the prime factorization for 60. And in order to simplify anything out of the radical, we have to have 2 of the same factor. So we have 2 factors of 2, so that's going to be enough to get us 1 factor of 2 outside the radical. And really, what this means is that 60 can break down as, we've got the 2 times 2, so that's going to be 4. The other remaining factors, 3 times 5, gives you 15. So 60 is 4 times 15, and the square root of 4 is 2. So another way of looking at it, it's still going to give you the same thing. And so now we have plus or minus 2 times the square root of 15. And then to finish this, we're going to move the 7 to the other side, so it becomes positive 7 plus or minus 2 times the square root of 15. So the same stuff that we were looking at yesterday. Oh no, there's a fun problem that we should do. Should have done this yesterday. But you know what? Today's a new day. So now is a good time to do it. So I hope that, for those of you watching the video, that you can see that these problems don't have to be super difficult. We just take our time, breathe, and remember that numbers are just numbers. So let's take a look at this next one. I have 1/10 x squared plus 1/15 x plus 1/6 is equal to 0. Now, a lot of students would see this, and they would see fractions, and they would say, all right, for this reason, I'm out. Well, let's see about what we can do with fractions. And this is going to kind of lead into some other stuff we're going to be talking about today. So we have a lot of fractions, and those typically get in our way. And you really don't want to take these numbers and throw them into the quadratic formula. I mean, you could, I just wouldn't recommend it. What I would recommend is clearing fractions. So in order to clear fractions, we want to identify the least common denominator. So if you look at all these denominators, what I think it might be the easiest way to do that for some of these smaller problems is take the largest denominator that we have, 15, and check, does 10 go into 15? No. So that means we've got to do another multiple of 15 until we get something that works for everybody. So 15 doesn't work, so let's try the next multiple, which is 30. Does 10 go into 30? Yes. All right, so I know that 30 is going to be great for 10 and 15. So as long as I now stick with multiples of 30, I should be okay. Well, let's look at 6. Does 6 go into 30 evenly? The answer is yes, so we have found our least common denominator, which is 30. Now there are two ways of clearing fractions. So what I'm going to show you is something that leads into a discussion that we're going to have a little bit later. Take this 30 and rewrite each of these denominators so that it is 30. So for example, I've got 10. What do I multiply 10 times to get 30? Well, that's 3. So I'm going to multiply both the denominator and the numerator times 3. So if I multiply times 3 over 3, that's a form of 1. And we know that multiplying times 1 doesn't change anything. So this will give me a denominator of 30, which is great. For the middle coefficient, 15 is missing a factor of 2, so I multiply times 2 over 2. And 6 is missing a factor of 5, so that we have a denominator of 30 there. All right, so when I work this out, I'm going to have 3x squared over 30 plus 2x over 30 and then plus 5 over 30. Now, the great thing about this is that everybody here has the same denominator. And if everybody has the same denominator, we can just kind of ignore that right now. If everybody has the same denominator, that means we can form the equation from the numerators. And you might say, well, what about the 0? That's not over 30. You know what? I can make that over 30, and it's still going to be 0. Another way of looking at this is you can multiply everything here times 30, which is going to cause all of those denominators to reduce away. And then what we're left with is this quadratic equation of 3x squared plus 2x plus 5 equals 0. Now that we have a quadratic equation established without all those kind of crazy fractions, let's go through our progression and see what we're going to do here. 1. Can I use the square root property? And the answer here is no. You've got x squared and you've got x, so too many x terms running around, that doesn't work. The second thing that we would try is factoring, using the zero factor theorem. And so this is where you might want to take just a moment to go off to the side and check out the AC method. So a times c is going to be 3 times 5, which is 15. And we'd be trying to find factors of 15 that add to 2. But there aren't any factors of 15 that add to 2. And don't even try to say, 3 and 5. Well, here's the thing. We want the absolute value of the factors to add to 2. And 3 and 5 don't add to 2. Now, if this had been a minus 5 instead, then yes, we'd use 5 and 3. But we don't have that. So the zero factor theorem doesn't work. Let's try completing the square. Well, right away we see that we have a lead coefficient that is not 1. Now we can get it to be 1 by dividing everything by 3. But when I do that, I'm going to create fractions here and here. And I don't want to create fractions. I just spent a bit of time getting rid of my fractions. So let's not do that. So even though I could complete the square, it's not in our best interest to do that. And so this is where we're going to lean on the quadratic formula. When nothing else works nicely, we go to the quadratic formula. So remember, quadratic formula. X equals negative b plus or minus the square root of b squared minus 4ac all over 2a. All right, so let's plug in what we have. So if we identify the a, b, and c, so a is 3, b is 2, and c is 5. So my solutions will be negative b, so that's going to be negative 2, plus or minus the square root. B squared, again, b is 2, and when you square that, you're going to get 4. Here's something to keep in mind about b squared. B squared is always going to be positive. Even if your b value is negative, when you square a negative, that's going to give you a positive. Now, be careful with this piece right here. I'm taking the entire part of negative 4 times a times c. So negative 4 times a is 3, c is 5. So I'm going to put all of that together. 4 times 3 times 5 is 60, but this is going to be a negative 60. That negative is very important. All divided by 2a, so 2 times 3 is 6. All right, so the rest of this is just a matter of simplifying. 4 minus 60 is negative 56, all divided by 6. Well, believe it or not, we can simplify that radical. And not just the I, right? So we've got the negative inside, so we know that's going to give us an I on the outside. But 56 can be broken down. I'm just kind of go ahead and jump to that for you. 56 can be rewritten as 4 times 14. Don't believe me? Check it out on the side and you'll see that that is going to work out. So the square root of 4 is 2. So we have negative 2 plus or minus. The 2 comes outside of the radical along with the I from that negative factor on the inside. So plus or minus 2i. And then 14 is remaining on the inside of the radical. And all of this is divided by 6. Now at this point you may be thinking, great, I'm done, let me just box this and move on. But wait, there is more. If you look at all the pieces that we have here, there is a common factor, and that common factor is 2. So we can reduce everything by 2, but you got to be careful about that. So you have 3 pieces here. You've got this guy. This 2i times the radical constitutes one piece because it's connected through multiplication, and then you've got 6. So what I like to show my students is this. Factor out the 2 in the numerator and see what you have. So if I factor out the 2, I have negative 1 plus or minus. Now if I factor a 2 out of that 2i squared to 14, I have just I times the square root of 14. I can't factor a 2 out of the radical, right? I have one factor of 2, and really if you look at that, you've got 2 times I times the square root of 14. So I'm pulling out the 2 factor that I can pull out. In the denominator, I'm going to write this as 2 times 3. It might seem a little bit unnecessary, but I want to make sure you guys see how we correctly simplify things. And so now you've got the factors of 2 that can reduce. And so our final answer is negative 1 plus or minus I times the square root of 14, all divided by 3. And so this is a problem that can be a little bit tricky, but it's just in terms of how we have to simplify it at the very end. Like I think applying the quadratic formula is not all that bad. And even simplifying the square root of negative 56 shouldn't be too much of a problem for us. It's making sure that we correctly simplify at the very end to get the answer that we see here. All right. So just a quick little review of quadratics. Yes, that's right. Yay, quadratics. Quadratics are great. So let's move on to something a little bit more fun. So we want to talk about rational equations. So rational equations are equations that contain fractions. In particular, where in the fractions you've got variables in the denominator, so it makes them a little bit more special. Well, I guess it doesn't have to be that way. I don't know why I'm saying that. Never mind. They just contain fractions. Yeah. So you could take something like this. Let's say x plus 5 over 3 is equal to 2x minus 7 over 5. This is a rational equation. Now, in particular, this is what we call a proportion. So I want to make sure we're very careful about how we say things. So uncut videos, yeah, so these videos are still, I'm not sure how long they stay up. I've never really done the streaming stuff, but yeah, you should be able to find them on my normal channel. I mean, I saw them there earlier today, the ones I did the past couple of days. So in a proportion, and of course the proportion is going to be where you have two fractions that are equal. In a proportion, the cross products are equal. So this is where we have to be very careful about things. So we say the cross products. Now a lot of times students start throwing around this phrase, cross multiply. Don't ever say that. Just don't ever cross multiply because it never makes sense. And students always mess that up. So in a proportion, cross products are equal. And so what I mean is that this product here So a times d is equal to this other cross product, b times c. And you might say, oh, but wait a minute, you just cross multiply. Like, no, I'm setting the cross products equal to each other. So a times d is what we call the product of the extremes, and b times c is the product of the means. So don't say cross multiply, because then later on when we start talking about, or not later on, but whenever people talk about multiplying fractions, and I say, how do you multiply fractions? And they say, you cross multiply. No, you don't. Not even close. You don't cross multiply with fractions. To multiply fractions, you multiply the numerators, you multiply the denominators. That's what you do. So let's put that into practice here. So that means I'm going to do this cross product of all of these guys. So I'm going to have this as 5 times x plus 5, and then this is going to equal the other cross product, which contains the factors 3 and 2x minus 7. So when we rewrite it this way, we no longer have big fractions to worry about. It's a nice, what should be a fairly easy equation. Now, right now, I can tell that this is going to be linear because I don't see that I have x times x or anything like that. Excuse me. So let's just go ahead and multiply and see what we have. So distribute. We get 5x plus 25. And on the right side, distribute the 3. 3 times 2x is 6x. 3 times negative 7 is negative 21. And so now we are stuck with just a linear equation. That means we want to get the variables to one side and the constants to the other side. Whenever you're doing this, you always want to make sure that you are moving the variable term first. That's the guy who's in control, not the constant. So I personally like to move my terms so that I have a positive coefficient for x. I mentioned this a couple of days ago, still going to be true now. So I'm going to subtract 5x to move all the variables to the right, and that's going to give me a positive coefficient for x. At the same time that I'm moving variables to the right, let's move our constant over to the left. So I'm going to add 21 to both sides. And let's see, we get 25 and 21, which is 46. And we have just x on the other side. So, hey, guess what? We're done. We got x by itself, and everybody's happy. Now, there is another way to solve this problem. All right, so I got to go back and remind myself what it was. All right, so if I take this again, x plus 5 over 3 equals 2x minus 7 over 5. Now, what we said is that when you have a proportion, cases where a times d isn't b times c, if you have a proportion, that means if you've got two fractions that are equal to each other, then it has to hold that a times d equals b times c. That's how that's one of those things that we just know that we have with fractions. If fractions are equal, if they mean the exact same spot on the number line, that means they're proportional, they're proportions, and so the cross products have to be equal. Now, what I want to do here is I want us to examine this guy and look at him the way we did the problem back over here. So in this problem, we had a bunch of fractions running around, and we got everybody to be the same denominator. And then we could kind of eliminate that denominator and just work on the numerators. So here, my common denominator is going to be 15. And that's pretty easy to discover because 3 and 5 are relatively prime. They have no common factors, so the common multiple for those guys is just going to be their product. So if I multiply each of these guys by their missing factors, the first guy is missing a factor of 5, so we put that in the numerator and denominator. So what you see there in red, 5 over 5 is 1. You're multiplying times 1, it doesn't change the problem. On the right side, this denominator was missing a factor of 3 so that it could become a denominator of 15. And you'll notice that these denominators are exactly the same. So I can just ignore those and work on the equation formed by these numerators. So something like that. And if you scroll back up, you'll see that's exactly what I had whenever I set the cross products equal to each other. So multiple ways to do the exact same problem. Okay. Let's try another one that's kind of like this, but might be just a little bit more difficult. How mean do I want to be? You know what? I'm gonna be nice right now. And I'm going to do this. Let's say x plus 5 over x plus 7 equals x over 6. All right. So if we go off of what we just looked at, we do have a proportion because we have a fraction equal to a fraction, which means that if these guys can ever be equal, and that's something I want to mention here. When we're solving equations, we start with the assumption that it can be equal, that it can be a true statement. And as long as it's true, there are certain things that we can do. Like we can add 49 to both sides. We can divide both sides by 3. But sometimes we end up at the very bottom where there's some kind of contradiction, which means everything should have worked out, but it didn't. Therefore, the original statement was false, or it can never be true. And that's where you run into situations where you might have, no solution. Well, here's the thing. Question in the chat, doesn't x over x cancel or, let's say, reduce each other out? I don't like saying cancel because when we hear the word cancel, we think of the number 0, right? But if I write this, if I write 9 over 9, you might think, oh, those cancel out. No, they reduce because 9 goes into 9 one time. So the answer here is 1, not 0. When you talk about variables and you say x divided by x, you might convince yourself that it equals 1. Or saying that they cancel each other out. No, they reduce, right? But there's a catch here. X over x does equal 1, provided that x does not equal 0. So if you take any number and you divide it by itself, you get 1, except for the case where you're doing 0 divided by 0. 0 divided by 0 gives you an undefined expression. Now, we can extend this to, say, more complicated expressions like x minus 2 over x minus 2. And just for the sake of argument here, I'm going to put parentheses around here. That way you can see that these guys are, that x minus 2 is a group. I don't want you to see this and go, oh, I'm going to cross out the x's and I'm going to cross out the minus 2's. It doesn't work that way. This will equal 1, again, under the provision that what you have here doesn't equal 0. So if I write this, if I write x minus 2 doesn't equal 0, that then means that x cannot equal 2. So if we look at x minus 2 divided by x minus 2, for any value of x that you choose, as long as it's not 2, then that expression will reduce to give you 1. But if you try to plug 2 into this, you end up with the undefined expression 0 divided by 0. Okay, now back to the problem at hand. Please do not look at this and say, oh, I can reduce those guys away. It doesn't work that way because the x here is not part of a product. It's not a factor, right? It's part of a sum. So you can't cross those guys out. What we'll do is it will set the cross products equal. So that means here we have 6 times x plus 5, and the other cross product is doing x plus 7 times x. So x times x plus 7. And now that we have this set up, it's just a matter of distributing And please, oh please, make sure that you distribute correctly. 6 times 5 is 30, not 35. Not that you guys would ever say that, but I've seen it happen. And then on the right side, x times x is x squared. Don't forget that you're doing x times 7 as well, so that's plus 7x. Now, surely you can finish this. I'm going to, give me 30 seconds. I need to get some water. But see if you guys in the audience can solve that, and we'll check your answers here in just a moment. All right. So what we have here is something that is quadratic. So really the first thing you want to do is get everything to the same side. So I'm going to just move these two guys from the left to the right. And you might say, well, why not move x squared to the left? Well, if I move x squared to the left, and since he is the guy with the highest degree, that's going to make my lead term negative, and that's going to cause more issues. So you want to keep your lead term, the guy with the highest power, you want him to be positive. Question, square root? I'm not sure what you mean by square root. Well, let's see. Let's get everybody to the same side first, and then we can reassess. So I'm going to move both of these terms from the left over to the right. And so we have, well, you'd have 0 on the left. You might as well just have that on the right. So I'm going to rewrite this as x squared. This is plus x minus 30 equals 0. One of the things you really have to watch out for with solving a quadratic equation is there's that temptation to see x squared and say, oh, that's x squared. Let me get x squared by itself and take the square root of both sides. That's only going to work out well if that is the only place you have your variable. But I've got x squared and I have a regular linear x term. So if I move the x to the other side and take the square root, then I have x in terms of the square root of x, and you're not getting x by itself. So I have everybody on the same side here, and let's think about how we go through solving a quadratic equation. The first thing is, can I use the square root property? Well, you have x squared and you have x, so no. The square root property is only when you have one instance of the variable, and that is a square. But I've got two places where I see the x, so that's not going to work. The second thing that I look at doing is the zero factor theorem. Can this guy factor? Well, you've got a lead coefficient of 1, so that's good for us. And then you want to look at the 30. Are there factors of 30 that have a difference of 1? And if you take a moment and think about it, you can come up with factors of 30 that differ just by 1. And that would be the factors 5 and 6. Those multiply to give you 30. And they have this difference here. They have a difference of 1. Now we have to get the right signs. So to end up with a negative 30, we have to have a positive and a negative. But to have a positive middle coefficient means the larger of those two numbers is positive. So that's positive, and then we have a minus there. And now at this point, we've got the factorization. It's set equal to 0, so we apply the zero factor theorem. So if you remember from yesterday, that means x minus 5 is equal to 0, or x plus 6 equals 0. And once we have those guys separated, then it's pretty simple to go straight to our answers. X equals 5, or x equals negative 6. So the reason we put everything on one side is to get a clearer picture of what's going to be the best method for solving this quadratic equation. So, and especially when you see that you've got x squared and x running around, that's kind of your clue that the square root property is already going to be eliminated and we can't use that. And in order to see if something can be factored, you have to have everything on one side and 0 be on the other side. Excuse me. That's the whole idea behind the name, the zero factor theorem. Have it set equal to 0 so that you can factor, and then you apply the theorem like we did here. If I'm going to complete the square, yes, I know I'd have to move the constant to the other side, but I still want to make sure that I can see if I've got the lead coefficient being 1 and an even coefficient in the middle. And in order to accurately and correctly use the quadratic formula, you have to have everybody on the same side so that you can identify your A, B, and C. If they're on opposite sides of the equation, you're going to get thrown off by a sign. So that's why we want to put everything on one side here. Now, if this were, like on the previous example, when I did the cross products and I multiplied everything out, you see that what we have here this is a linear equation. So when it's a linear equation, this is where you separate your variables on one side and you put your constants on the other side, because you'll be able to put all of those variable pieces together and you're going to be done. But when you have something that's quadratic, you can't just separate the variables from the constants, because you're going to put all those guys together to consider, to consider factoring or completing the square of the quadratic formula. But there's one last little piece we have to talk about here. Sometimes the answers we get, we don't actually get to include. So I'm just going to erase this stuff real quick. So when it comes to solving rational equations, you have to be mindful of restricted values. In a restricted value, this is going to be any replacement of the variable that makes the denominator equal 0. So if we look at this, the original equation here, just focusing on those denominators, x plus 7, could that ever equal 0? And the answer is yes. So here, our restricted value is going to be x equals negative 7. Because if you were to plug negative 7 into that expression on the left, you end up with a denominator of 0. And when you have a denominator of 0, then your expression is undefined. On the right side, your denominator is 6. 6 is a constant, which means it's always going to be 6, and there's no chance for that guy to become 0. So this was the only restricted value that we had to worry about. So let's look at our answers. Our answers were 5 and negative 6. Neither one of those is a restricted value, so as long as we have done everything correctly and we've paid attention to our signs, then we end up with both of them working out for us. Again, it doesn't always work out that way, but in this example it does. All right, let's try one that's a little bit more complicated. But again, don't let me saying complicated scare you away. As long as we take our time and we breathe, we can get through these problems. So let me take this. 6 divided by x squared minus 8x plus 15 plus 3 divided by x squared minus 4x plus 3 is equal to 5 over x squared minus 6x plus 5. Now, it looks like there's a lot going on here. But let me remind you of this. So, if you have two fractions that have the same denominator, okay? Oh, I realized that. What's going on here? There we go. So if a over c equals b over c, then that means that those numerators have to be equal. So if you have two fractions that are equal and they have the same denominator, then the only way those two fractions can be equal is if their numerators are also equal. So what we can do here is that we can rewrite all of these fractions to have the same denominator. And if they have the same denominator, then we set the numerators equal and we solve. And we did that back over here. We talked about how with this particular equation, I put in the missing factor so that the denominators were exactly the same. And then what was in the numerators, that became my new equation. Now I'm going to do that here on a much larger scale. But it's going to be okay. In order to do this, we have to be able to look at these quadratic denominators and factor them correctly. So make sure you pay attention to your signs. Take a moment to check it by multiplying it out. Now, I feel like I'm being nice here because everything is just 1x squared. You don't have like 2x squared or anything weird going on, so we should be able to nicely factor these guys. So factors of 15 that add to 8 are 3 and 5. And so this denominator factors as x minus 3 and x minus 5. In the middle, we need factors of 3 that add to 4, so that's going to be 1 and 3. So that's actually going to be x minus 1 and x minus 3. And then on the right side, we need factors of 5 that add to 6. Well, the only options there are 1 and 5. So that's going to be x minus 1 times x minus 5. So once we have all of the factorizations done, we go in and we put the factors that are missing. So if I look at that first denominator, x minus 3 and x minus 5, and you compare that to the other denominators, you'll see that there's a factor that everybody else has that he does not have. And that missing factor is x minus 1. So I'm going to put that factor that's missing down in the denominator. But if I do that, that changes the problem unless I also multiply the numerator times that factor. So essentially, I've multiplied the top and the bottom times the same factor, which means I've multiplied this fraction times 1. For the fraction that's in the middle, you'll see that the factor that everybody else has that he doesn't have is the factor of x minus 5. So put that in both the numerator and the denominator. And then finally, on the right side, the factor that everybody else has that he's missing is x minus 3. And again, I put that in both the numerator and the denominator. And what I hope that you can see is that this denominator and that denominator and that denominator, these guys are all the same. So now that we have created an equation where all of the denominators are the same, we can rewrite our equation just from the numerators. So I'm going to go one step at a time here so I don't make a mistake. So we got 6 times x minus 1 plus 3 times x minus 5 equals 5 times x minus 3. And this is the equation I'm going to work on solving. Right? I don't need to make things extra difficult. And you might say, well, why didn't you just distribute as you were bringing the stuff down? Well, because sometimes there are negatives, and I just want to make sure that I distribute correctly, right? I am not above making a mistake. So sometimes I have to really just slow down, take my time, and be very deliberate about everything that I do, even if it causes me to take an extra step. So now let's distribute. 6 times x is going to give me 6x, and 6 times -1 is -6. Make sure that you are distributing correctly. If you need to draw the arrows to make sure that you are multiplying everything and you're not skipping anything, then do that. All right, and so let's do the next one. So we've got plus, distribute here, that's 3x minus 15, and on the right side we get 5x minus 15. Now, the best thing that you can do here is to go ahead and combine your like terms on either side, right? So on the left side, 6x plus 3x is 9x. -6 and -15 combine to give you a -21. On the right side, there's not anything here to combine, so we just bring those guys down like that. All right, let's keep on going here. Once we've cleared out those denominators, or we look at the numerators and we've distributed and all that stuff, see what kind of equation you have. So I can see that this guy here is a linear equation. And when it's linear, x is going on one side, constants go on the other side. So I'm going to move my variable terms so that I have a positive coefficient, and I accomplish that by subtracting 5x on both sides. And I'm going to also move this 21 over to the other side, like this. And now I have 4x is equal to positive 6. And the last thing to do here is to divide both sides by 4. So x equals, make sure that you reduce correctly. There's a common factor of 2, so it reduces to x equals 3/2. Now, before we box this guy, I do want to make sure that we pay very close attention to any and all restricted values. What were values that we were not allowed to have here because it would cause our denominator to equal 0? Well, if you scroll back up and you look at your factorizations, here for that guy, x minus 3, the restricted value was 3. For x minus 5, if you set that equal to 0, you get 5, and the last guy would be 1. So as long as I don't have any of these guys as a solution, and as long as I did my work correctly, then this should be my answer. And that's all there is to it. So we want to look at finding the factorizations, put in those missing factors, and once you get everybody to have the same denominator, you rewrite your equation based on what you have in the numerators. All right, so you're asking for another example? Sure. This one's going to be a little bit more interesting, I think. All right, so let's take this. X divided by x squared plus 11x plus 28 plus 2 divided by x squared plus 7x plus 12 equals 8 over x squared plus 10x plus 21. It looks very much like the last problem that we did, and we're going to approach it the same way. We want everybody to have the same denominator, and the best way to do that is to focus on the factors, like what pieces make up each of these denominators. So we're going to look at them one denominator at a time, factor them, and then put in the missing factors. So, for this first denominator, and please notice that all these guys are just x squared. So we should be able to break these guys down nicely as x times x, and then concentrate on the constant term to see the factors of the constant that will give us the middle coefficient. So factors of 28 that give us 11 will be 4 and 7. Everybody here is positive. For the middle denominator, let's see, x squared is going to break down as x times x, and then factors of 12 that add to 7. So it's going to be a plus 3 and plus 4. Now, at this point, you should already see some factors that are common. Like in those first two denominators, you already see they both have x plus 4. That's kind of a clue that you're on the right track. Now, for the last one, I'm expecting him to have factors that we've already seen. Now, if every single denominator has two completely different sets of factors, especially if it's a problem that I'm giving you, then you've probably done something wrong. So over here, we need factors of 21 that are going to give us 10. And that would be 3 and 7. Now, if you said 7 and 3 and you wrote the factorization in a different order, that's fine, because it was, as we talked about before, with multiplication, the order doesn't matter. So if you write x plus 7 times x plus 3, it's the same thing. All right, now let's put in those missing factors. In the first denominator, what's missing that everybody else has? And when you start to compare, you see, oh, he's missing the factor of x plus 3. But I have to put that in the numerator as well. You can't ignore that. Whatever change you make to the denominator, you make the same change to the numerator, and it has to be in terms of multiplication. Like, you can't just add or subtract things. I'm putting in a factor, that's multiplication, of x plus 3. The middle fraction is missing the factor x plus 7. That's what the other two denominators have that he doesn't have. And finally, this guy over here is missing the factor of x plus 4 that the first two denominators have. So we see here that all of these denominators, although the order is not the same for those factors, each of these denominators contain the same set of 3 factors. So now we rewrite this using our numerators. So x times x plus 3 plus 2 times x plus 7 equals 8 times x plus 4. All right, and then from here, step by step, right? We got to distribute carefully and correctly. So we have x squared, and don't forget that x times 3 is 3x. Again, I've seen a lot of students just do x squared plus 3, they forget to fully distribute. And then we have plus 2x plus 14 equals, over here we have 8x plus 32. Now, a quick look at this and you'll see that we have an x squared term. And that's the only x squared term that we have, so it's not like he's going to be eliminated or canceled out with anything else. So we do have something that's quadratic. And because we have something quadratic, then we should be thinking about solving a quadratic equation, which means we want everybody to be on the same side. Now, before I do that, you might find it helpful to go ahead and combine like terms here on the left. 3x and 2x is 5x. And so we do this before we bring over these terms from the right side. Now, you don't necessarily have to do it that way. I'm doing that so you can see every single step and you understand where everything comes from. So I move everything over to the left side because I do have something that's quadratic, and this is how I want things to look at the very beginning for solving a quadratic. So we end up with x squared minus 3x minus 18 equals 0. All right, make sure that you pay attention to your signs, that you add correctly. So with this being quadratic, let's think about our quadratic progression. Can I use the square root property? Well, I've got x squared and I have x, so the answer is no. Can I factor this? Well, let's see. My lead coefficient is 1. Look at the constant. Are there factors of 18 that have a difference of 3? And I hope that we can see that the answer is yes. We use 3 times 6 or 6 times 3, and that's going to give us exactly what we want. Now, we know that to get a negative 18, we need a positive and a negative, but we also need to have a negative for the middle coefficient, which means the larger of these two factors must be that sign, so the negative is going to be for the 6, and the 3 is going to be positive. All right, if we finish this, so from this factor we get that x equals negative 3. From the other factor we have x equals positive 6. And you might be thinking, yes, sweet, let's circle these and move on. But hold on. We've got to make sure that we remember to check for restricted values. Were there values of x that would cause a denominator to be 0? And the answer is yes. Look at these factors. We've got 3 factors. Each one of them could be 0 depending on what value of x you plug in. So for x plus 4, the restricted value is negative 4. For x plus 7, the restricted value is negative 7. And then for x plus 3, the restricted value is negative 3. So if we have any of these guys showing up as solutions, then we can't actually include them in the solution set. And we see that we have an issue with this guy right here. This is a restricted value. So he is not included as part of the solution. What he is, or what we call him, is we call him an extraneous solution. It doesn't mean that we did anything wrong. It just means that when we try to plug this answer back into the original equation that has its own kind of restrictions, it doesn't work out and it gives us something that's undefined, or something that it just gives us a bit of an error. But x equals 6, that guy's going to be fine. All right, so you're asking for an equation you can solve on your own. All right, I'm going to throw something up here. You guys can write it down, but I'm going to move on to do some other stuff. Let's take x over x squared plus 15x plus 50 minus 4 over x squared plus 13x plus 30 equals 2 over x squared plus 8x plus 15. Yeah. Let me just see something real quick. So you guys can write that down, and yeah, while you do that, hold on a second, what was that? I'm going to go ahead and get the answer. Wait, what was that? Nope. That was number that. Okay. Sounds good. All right. So I'll give you the answer to that at the end of this video, as long as I remember. I might forget. Sometimes I'm forgetful. All right, so these were rational equations, equations that contain fractions. The next thing we want to look at will be radical equations. As you might expect, these are equations that contain radicals. So things like square roots, cube roots, and the like. Sometimes they include some extra weird stuff as well. Well, that is not what I thought it was. All right. So the key thing to understanding this is what's called the power property. And the power property says this. It says all solutions to the equation A equals B can be found among solutions to the equation A to the n equals B to the n. In other words, if you raise both sides of the equation to the same power, any solutions that were present in the original equation will be found among those new solutions. Now, by doing this, sometimes you come up with extraneous solutions. Again, not that you did anything wrong, but because of the limitations of the original expression, things just don't work out. As with a lot of things that we'll see, you have to isolate the radical first before you apply powers on both sides. So, for example, if I take the square root of x plus 3 minus 7 equals 2. In order for us to solve this and solve it well, I need to isolate the radical. And so that's as simple as adding 7 to both sides. So now I have the square root of x plus 3 equals 9. Now that the radical is by itself, we want to apply a power to both sides so that we can undo that radical. So think about how you read this. This is the square root. So if I square both sides, the square and the square root are acting as inverse operations, and that's going to kind of cancel each other out or reduce them away. So x plus 3 equals, so the square and the square root, those dissolve each other away. On the right side you have 9 squared, and so that is just 81. And then we look at what we have left over. This is just a linear equation. X plus 3 equals 81. Subtract 3 on both sides. So you get x equals 78. Now, before you box this, you want to make sure that you do check this against your original equation. I mean, it should work out. Like, we didn't do anything weird, nothing strange happened. But always take the time to check your work, especially when you're dealing with roots that are even. I mean, like square roots, fourth roots, and so on. So I want to check that if I plug in 78 for x, does all of this equal to? Well, we end up with the square root of 81 minus 7, which is 9 minus 7. It equals 2. So yes, it does work out. So now I can safely box this answer. And that's really all that we're doing here. So please, oh please, do not try to make it more complicated than that. Now, what I tend to do as a teacher is I try to add a bunch of extra stuff to see if students can see through it. So, for example, if I were to write (56) minus 5 times the cube root of 7x plus 22 is equal to Hold on a second. Let's do 11. Now, one thing to note here is that this is the only place that you have your variable, right? So you're going to hear me say you peel away the layers. And we did that before when we were solving by using the square root property. So this is a little bit different, but you're still going to peel away those layers until only x remains. Now, what should be standing out to you in this problem is the fact that you have a cube root. So the radical should stand out to you. That tells you that we are dealing with a radical equation, and so we are not thinking about the quadratic formula or completing the square. We're thinking about, how do I take care of the radical? The first thing you do is to get the radical by itself. And if you go, like, I just don't know how to do that, well, think about it like this. If I were to write 56 minus 5 w equals 11, can you solve that for w? I would like to think you could. And if you can solve that little equation there in purple for w, you can solve this equation by getting the radical by itself first. So peel away the layers, starting with the thing that is least connected to the variable, which is the 56. He's all the way out here, not even close to touching that. So we subtract 56 on both sides. We now have negative 5 times this cube root is equal to negative 45. All right. Now, we don't quite have the radical by itself because of that, that factor of negative 5. So we undo the negative 5 by dividing by negative 5. So those guys reduce to give me a 1. And I have the cube root of 7x plus 22. On the right side, that is just positive 9. Right? No big deal. Now, we can't do anything with the x until we get rid of what's enclosing that x, and that's going to be the radical. So, the power that I use to undo a cube root will be the third power. So the power that you use is going to match the index, and it's going to be, yes, so when you think about when we were doing this stuff a couple of days ago with radicals, let's see. If I were to write the cube root of x, that really meant x to the 1/3 power, right? And so the 1/3 power, I guess like the opposite or so power of that would be raising to the third power. And that's what we're doing here. So we end up with 7x plus 22 equals 9 to the third. So if you don't know 9 to the third, then you build that 9 times 9 times 9. And, perhaps you write it out like this, just to make sure you don't make any careless mistakes. So 9 times 9 is 81. Times 9, and these guys come together to give you 729. So 729. And now what you have here is a nice linear equation. So you got rid of the radical, you did the power property, and then what's left is a linear equation. So you solve it using linear methods. So subtract 22 on both sides. And we have 7x is equal to 707. And then we divide both sides by 7. And you do the division here, you get x equals 101. There you go. Not too bad. So see the question there, you got to x squared minus 3x equals 0. Actually, you didn't. You're talking about the problem that I put on the other page. Be very careful. Pay attention to your signs. You're missing something. Trust me, and I know exactly what it is. make sure that you're showing each step. Make sure that you distribute correctly and carefully, especially when it comes to signs, especially there in the middle when you got the -4. That's on the previous problem, or this guy right here. Did you pay attention to the negative, and did you distribute this as a -4? Perhaps not. I'm just guessing. All right. So sometimes these radical equations can definitely be a little bit more complicated. Now, you might argue with me that, oh, this one was complicated. But really, was it? You're just trying to get x by itself. So move over the 56. You get rid of the -5. You raise both sides to the power, just peeling away these guys one letter at a time. But now, what if I do this? If I say x minus 5 is equal to the square root of 3x minus 5. Now, when we have an equation that contains a radical, we've got to get the radical by itself. Now, that's already done here for us. Now, I don't want you to look at this and go, oh, look, there's x minus 5. I just have to add 5 and I've got x by itself. Well, you don't, because on the other side of the equation, you would still have x inside of a radical. So it's not helping your cause at all. But what we can do here, we have the radical by itself. So this is where you want to go ahead and raise both sides to a power that's going to eliminate the radical. Since I'm dealing with a square root, I'm going to raise to the second power. Now be careful. What you do to one side of the equation, you do to the other side of the equation. You do not distribute a square. So don't go, oh, this is x squared and -5 squared. That's not how it works. You're squaring that binomial. And we talked about this the other day. That if you have a binomial that's being squared, you get a squared plus 2ab plus b squared. But if you don't like that, you could always take x minus 5 squared and do x minus 5 times x minus 5. Multiply all of that out. FOIL, box method, whatever floats your boat. But if I apply this shortcut over here, that means my first term is going to be, here's your a and here's your b. First term is going to be a squared, so it's going to be x squared. Then the 2 times a times b. Think about doing a times b, that's going to be -5x, and then you double that, so that's going to give you a negative 10x. And then you square the -5, and that becomes a plus 25. So if you had done x minus 5 times x minus 5, this is exactly what you would have there too. Now, on the right side, you square the square root. Those guys reduce away from each other, and we have 3x minus 5. And so now what we have is something that is quadratic. So it's quadratic, and you've got x squared, and you have x running around here, so that means probably not square root property. So we should be thinking about factoring next. And if you're going to factor, you need everything on the same side of the equation. Just like the equation that's there in chat, you moved everything over so that you have it equal to 0. And now we're going to factor. So I've got to move the 3x over, so it's minus 3x on both sides. And I'm going to add 5 on both sides. And so now we have x squared minus 13x plus 30 equals 0. It's quadratic. We already know that we can't use the square root property. What about factoring? Are there factors of 30 that add to 13? And it should only take a moment for us to realize that those factors are going to be 3 and 10. So x minus 3 times x minus 10 equals 0. So from here we get x equals positive 3, and the other one is x equals positive 10. Now again, there's this temptation that we just circle these guys and we go on. But because we started with a square root in our equation, we have to check to see, do these guys work? Because the square root symbol that's in the original equation is not a plus or minus thing because we didn't put it there. It was there from the beginning. So that square root sign just means the positive or the principal square root. So we have to check these guys. So let's check x equals 3 and see if this is true. So if I plug in 3 for x, does this side equal the other side? Well, here on the left, I get -2. And on the right, let's see, this is 9 minus 5. Does -2 equal the square root of 4? The answer is no, right? If that square root symbol could have allowed for positive and negative, then it would have worked. But it doesn't. So this guy here is extraneous. Now, don't take this to mean that x equals 10 is automatically going to work. It could be that neither one of them works. It could be that they both work. So we won't know until we actually check. All right, so let's check x equals 10. I've got 10 minus 5. Does that equal 3 times 10 minus 5 in the square root? Well, 10 minus 5 is 5. This is 30 minus 5, which is 25. So does 5 equal the square root of 25? The answer is yes. So that means that x equals 10 is my only solution here for this problem. All right, so yes, in the chat for that other equation, 8 is the right answer. And it's good that you pointed out that -5 is a restricted value. So yes, good call. Gotta watch out for those signs though, right? All right. Now, like, we can keep doing these kind of problems like this with the simple radical, but they all kind of get to be a little bit samey. Let me show you some questions that will, well, they definitely mess up my students. And so if I have any of my students that are out there watching this right now, whether live or you're watching it afterwards, these are questions that you see on the test, you see them in the homework. So take a deep breath and let's see what we can do here. So if I have, let's say, x plus 9 to the 3/2 is equal to, let's just say, 125. Believe it or not, this is still considered a radical equation, and that's really because of that power, the power being a fraction. So a rational power is indicative of a root. So we didn't really talk about this the other day. We're talking about powers, but here's something that you need to know. X to the 1 over n power means the nth root of x. So when you have a power that's a fraction, the denominator of your fraction will be the index for your radical. It's as simple as that. If I have a power that is a fraction, say m over n, you would still have the nth root of x, but then you would raise that whole guy to the m power like that. And that's all there is, right? The denominator in your power tells you the index. The numerator is just the normal power itself. All right, so what I want to do is I want to get rid of that 3/2 power. And the way that I do that is that I raise both sides of the equation to the reciprocal power of that. So I'm going to raise it to the 2/3 power. So raise both sides here to the 2/3 power. Now, when you have a power to a power, remember that a power to a power, you would multiply those powers. But if I'm raising it to its reciprocal, a fraction times its reciprocal is just 1. Again, this is why I'm choosing to use the reciprocal, so I end up with just x plus 9. And then on the right side, I have 125 to the 2/3. So to make sense of this, we're going to rewrite this using the radical notation, the examples that I have here on the right side. So having a denominator of 3 means I'm dealing with the cube root of 125. The numerator in the power of 2, means I'm going to have this squared. You could look at this as 125 squared and then apply the cube root to that. But it's typically easier for you to go small before you go big. Because if I ask you what's the cube root of 125, you probably know that that's 5. However, if I ask you to square 125, you probably don't know what that is. You're going to get a huge number, and then you're going to have to figure out, what's the cube root of that. So let's not deal with big numbers if we don't have to. So x plus 9 equals cube root of 125 is 5. And then, of course, 5 squared is 25. And so you got this nice, this is, come on, you can't get much easier than this. X plus 9 equals 25. Subtract 9. And we have that x equals 16. And that's it. Like, there's nothing else for you to do there. Now, I can make the problem look a little bit more difficult by adding a bunch of embellishments. So I could say, suppose I have 5x minus 7 raised to the, maybe the 5/3 power minus 9 equals 23. So I'm just adding more junk here, and you have to be able to figure out what's going on. The big thing that should stand out to you is the fact that we've got something in parentheses raised to a power that's a fraction. Well, a rational power indicates a radical equation, so we have to get that guy by itself and then raise both sides to the appropriate power. So let's do that. I have to first move the 9 to the other side. So you're gone. So 5x minus 7 raised to the 5/3 power equals 23 plus 9 is 32. And in order for me to get the x by itself, I can't even do anything with the 5 or the 7 until I take care of that power that's containing all of that stuff. So I raise both sides to a power that is the reciprocal of that. So raise both sides to the 3/5 power. And over here as well. So we end up with just 5x minus 7. And on the right side, we have 32 to the 3/5. So we need to rewrite that as a radical to help us really understand what's going on there. So remember, the denominator of your power is the index for your radical. So we are really looking at doing the 5th root of 32, and then we're going to raise that guy to the 3rd power. Again, this is the easiest way to do that. Make the number smaller before you make it bigger. Now, maybe you don't remember all of this, but let me remind you that 2 to the 5th is 32, which means when I try to figure out what is the 5th root of 32, I'm trying to figure out what to the 5th power gives me 32, and the answer there is 2. Right? That's how these expressions are connected. All right, so we have 5x minus 7 equals 2 to the 3rd. But 2 to the 3rd is really equal to 8. And then we add 7 to both sides. So 5x equals 15, which means x equals 3. And that's it. There shouldn't be anything else that we have to worry about doing for this problem. And I don't know what else to say. That's it. Now, I added extra stuff here, but the steps are very similar to what we would have done with maybe solving by using the square root property. You would get the square by itself, so you could then use the square root property. Here, I'm getting this power guy, this guy in the parentheses by himself, so I can raise both sides to an appropriate power to undo that. And then what's left over is a linear equation. Yeah, you got to figure out 2 to the third, but it's still just a number. Now let me show you where things get a little bit messed up. So suppose I give you this. And I say x to the 2/3 equals 16. I mean, seems simple enough, right? I just have this one instance of my variable as to the 2/3 power, and I just need to get rid of the power. So if I look at what happened in those previous examples, it seems like I should just raise both sides here to the reciprocal power, which is 3/2. So you get raised to the 3/2, and you get raised to the 3/2. On the left, we just get x. On the right, as I try to rewrite this using the radical, you'll see that my denominator is 2, so that tells me I'm dealing with the square root of 16. And this is where we've got to be very careful. This square root wasn't there before. This square root is something that I introduced to the problem whenever I raised both sides to the 3/2 power. And because I'm the one who introduced it, I have to put in a plus or minus. And then this is going to be raised to the 3rd power. And so this is what a lot of students forget to do. So when I'm raising both sides to a power, and we have here an even denominator for the power, that indicates an even root, indicates a square root, and you have to have the plus or minus. So then x is equal to plus or minus the square root of 16 is 4. And then I cube this. So if I cube a positive, I get a positive. If I cube a negative, I get a negative. So then just worry about doing 4 to the 3rd, which is 64. And you would see that if you chose either of these guys and you check them out, it would work out. Now, strangely enough, I have students that say they check and they say, oh, negative 64 doesn't work. You know what? Let's do it for both of them. If I do 64 to the 2/3, just by plugging it in, right? Let's check this. This denominator of 3 for the power tells me a cube root of 64, and then I would square that. The cube root of 64 is 4, and 4 squared is 16. So clearly 64 checks out. The second root of square root. And we don't really say second root, we just say square root. If I plug in negative 64 into this, this means that you're doing the cube root of negative 64, and then you square that. Well, the cube root of negative 64 is negative 4. Now that's in parentheses. And then you square that, and you still get positive 16. So we have two solutions here, positive or negative 64. Nope, don't ever say that you're dumb. Don't say that you're stupid. Don't say, I've got a stupid question or anything like that. No. Sometimes we make errors, we make mistakes, but it's nothing to call ourselves names over, right? And just because you think that the question you have is so simple, just ask the question. Don't put any extra qualifiers in front of it. Just say, I've got a question. Now, let's make this extra fun. So still the same kind of concept, but let me just add a couple of extra layers here. But you'll see that even if I add more layers, the concept is still the same. Bigger numbers, they're still just numbers, who cares? All right, so if I do, I gotta make sure things work out well. All right, so let me do 8x plus 17 to the 2/3 power. You know what? Nah, let's move to the 2/5 power. Let's have some fun here. And let's say this is equal to 9. Well, you'll see that the set of parentheses is already by itself. This is the guy, the big guy in question. And now we need to apply the power property. So to undo the 2/5 power, we're going to use the reciprocal of this and raise it to the 5/2 power, like so. Now, be very careful how you write this. We need to understand, I'm going to put this in red, this is not 9 times 5/2. It's not that. It's 9 to the 5/2 power. So on the left side, we have 8x plus 17. On the right side, this denominator of 2 tells me we're dealing with the square root of 9, but I introduced the square root because I raised to the 5/2 power. That means I have to have plus or minus. And then all of this is raised to the 5th power. Okay? So the first step there is understanding how we apply the power property on both sides and why we're choosing to use the reciprocal power. That's so that I can eliminate the power that's already present there on the left, the power of 2/5. On the right side, I have to make sure that things stay balanced, which is why I also raise that to the 5/2 power. That denominator of 2 in the power means that I'm dealing with the square root. The numerator tells me that the bigger power that I have on the outside. And since it's a square root, I've got plus or minus. On the previous page, you saw that I did say that the 5th root, no plus or minus. Or I have the cube root, no plus or minus. If it's an even root, then I have to have the plus or minus. All right, so just got to work this stuff out. Now let's see, we've got 8x plus 17 equals, so the square root of 3, nope, the square root of 9 is 3, so plus or minus 3 to the 5th power. And then 8x plus 17 equals plus or minus 3 to the 5th is 243. Now at this point, you see that we have a plus or minus, and we don't have radicals, we don't have anything imaginary, so that means there's going to be extra work for us to do here at the end. Let's just go ahead and get x by itself. So we'll subtract the 17. Again, put that in front of the plus or minus. And then we'll divide both sides by 8. And so now we have to separate this and finish to get our two solutions. All right, so one of these is negative 17 plus 243 divided by 8. And the other one is negative 17 minus 243 divided by 8. And so here, this is just an exercise of simplifying fractions. Let's make sure I don't make a careless mistake here. So this is going to be 226 over 8. Yep. And this is going to be negative 260 over 8. We can reduce these. Let's see, this guy right here, I'm running out of room. I did not space this well. This is 113 over 4. And this guy becomes negative 130 over 4, which can reduce further to give me negative 65 over 2. So there we go. There are our two answers. Not too bad. Again, it's a matter of taking our time and knowing what the symbols mean. Okay. Now, one of the last things I want to talk about today will be solving equations that are quadratic in nature. All right, so equations that are quadratic in nature, they are almost like they're quadratic, but not quite. But they have certain quadratic tendencies to them. So these are going to be equations that look kind of like this. AU squared plus BU plus C equals 0. Where U is some variable expression. The key thing here is noticing that you're going to have a constant term just like a normal quadratic, and then you're going to have this guy right here. You're going to have some variable expression, and you're going to have that same variable expression here, but he's now going to have double the power. Now, some of these equations that are quadratic in nature are fairly simple, and you can just factor them. There's not a whole lot to them. For example, if I take x to the fourth minus 7x squared plus 6 equals 0. Now, what makes this quadratic in nature is that you have your constant term 6, you have x squared, and then this x to the fourth is x squared with double the power. So that makes them quadratic, because doubling that power means you're squaring that. Now, I want you to imagine if I had given you this. If I had, let's say, w squared minus 7w plus 6, and I asked you to factor that. Well, I hope that we could see how this becomes w minus 1 times w minus 6, right? No big deal. You take that w squared and you split that up evenly as w times w, and then you work on finding factors of 6 that are going to give you the 7. Well, we do the same thing here, even though it's x to the fourth. Think about how you would evenly split up x to the fourth, right? Split it up evenly. You get 4 factors of x, so split it up and do 2 groups of 2. So you'd have x squared and x squared in much the same way we took w squared and we did w times w. Now let's find factors of 6 that add to 7. So that's going to be 6 and 1, and both of these guys are going to be negative. And you'll see that whenever you multiply everything out, you're going to get some good numbers here. You've got x squared times x squared, which is x to the fourth. Negative 6 times negative 1 is positive 6. And when you check on the inside here, that's negative 6x squared. On the outside is negative x squared. And altogether, that's negative 7x squared. So it all gives you, it all works out to be the original equation. But we need to actually finish this though. We can now use the zero factor theorem because we have a product equal to 0. So we can split this up and say x squared minus 6 equals 0, or x squared minus 1 equals 0. So now you have 2 smaller quadratic equations to solve. Well, think about what you would do. If I've got x squared minus 6 equals 0, I need to get the x by itself, and he's only there in one spot. So I'm going to use the square root property. So x squared equals 6. And then to get the x by itself, I'm going to apply the square root property. Don't forget the plus or minus. So x equals plus or minus the square root of 6. Do the same thing for the other part of this equation. So move the 1 to the other side. Apply the square root property. Don't forget the plus or minus. And then x equals plus or minus 1. Now, if you go back to the original equation here, you see you have x to the 4th. This is a polynomial equation, so the degree tells you how many solutions you're supposed to have. It's a degree of 4. I should have 4 solutions, and I do. Plus or minus the square root of 6 is 2 solutions. Plus or minus 1, that's 2 more solutions. So we have 4 solutions to this equation altogether. Not too bad. And for this one, it's all about factoring. Actually, for most of them, it really does come down to factoring. It's not always going to be that way, but yeah. All right, so let's try this one. X to the 4th plus 10x squared plus 24 equals 0. This is another one that is quadratic in nature. You see you've got your constant term, you've got your squared term or your x squared term, and then you have double that power for the first term. Well, let's see if we can factor this just like we did the last one. With x to the 4th, my expectation is that I can break this down as x squared times x squared. And now I want to find factors of 24 that have a sum of 10. So hopefully 4 and 6 jump out at you. So we'll do 4, we'll do 6. The signs that we want to use here, since we need to get a positive 24 when we multiply and get a positive 10 when we add, these guys are both going to be positive. So the first part here is recognizing, yes, I can factor. Do that, everybody's happy. And because you have this factorization equal to 0, we use the zero factor theorem. So either x squared plus 4 equals 0 or x squared plus 6 equals 0. Just like the last problem, isolate the x squared so that you can use the square root property. So x squared equals negative 4. Take the square root of both sides. We introduce the square root. We have to have the plus or minus here. So x equals plus or minus, now be careful. You do have the square root of 4, so that's going to be 2, but you also have the negative inside, so this is going to be plus or minus 2i. And we talked about this yesterday. Yes, you can have imaginary solutions. That's fine. For the other factor, x squared equals negative 6. Take the square root of both sides. So x is equal to plus or minus 6. Unfortunately, we can't do anything with that. So all we can do is take out the imaginary unit I, and 6 stays inside. Again, we were expecting to have 4 solutions, and we do have 4 solutions. All of them are imaginary, but they are our solutions, right? So don't go running off saying, oh, there's no solution. No, there are solutions. There's 4 of them. They were just all imaginary. Now, sometimes we have situations that are a little bit more complicated. And so we're going to do this thing called a use substitution. For example, if I take this, if I say 3x plus 5 over x minus 7 squared plus 2 times 3x plus 5 over x minus 7. Let's see, minus 35 equals 0. I want to solve this. Now, it is a rational equation because I've got fractions in here. But even better than that is that it is quadratic in nature. So let's make sure we identify the pieces that tell us it's a quadratic in nature kind of problem. You've got a constant there at the end, okay? You have some variable expression here. You have that same variable expression, and it's double the power. So here's what we're going to do. We are going to do what's called a u substitution. So I'm going to create a new variable, let's call it u, and I'm going to let this guy stand in place of the expression 3x plus 5 over x minus 7. So instead of me writing that guy all the time, we're trying to work with that, I'm going to let this other variable u represent that. And if I make that substitution, then my equation now becomes, well, instead of 3x plus 5 over x minus 7, that's just u to the second, plus 2, again, this is just u, and then minus 35 equals 0. Now, I don't know about you, but this equation looks a whole lot nicer to work than what we had at the very beginning. So let's keep working with this. Now, notice that I do have a different color, and I want to make sure we are aware of that. That different color signifies to me that I'm not, like, if I solve this, I'm not going to be done. Because I'm going to have to go back to my original black color and not this new pink color. But while I'm working this other realm with the u and not the x, I'm going to keep this new color. So I've got u squared plus 2u minus 35. You'll notice this guy does factor. We're going to break down the u squared as u times u. And let's find factors of 35 that have a difference of 2. So those factors would be 5 and 7. To end up with a positive 2 in the middle, I'll need the 7 to be positive, which makes the 5 negative. Okay, again, I'm still in pink. Even when I solve this guy, I'm solving it for u right now. So u minus 5 equals 0 means u equals positive 5. Or, from the factor u plus 7, we'll get u equals negative 7. All right, now we're not done. See, this is what u equals. But I don't want the variable u. I want to go back to what it was, or what it was representing, which was that expression at the top there, 3x plus 5 over x minus 7. So now I'm going to go back to black and rewrite this as 3x plus 5 over x minus 7 is equal to 5. And this is my new equation that I'm going to solve. Now, I'm going to actually make 5 over 1. And I'm going to turn this into a proportion. And in a proportion, the cross products are equal. So this cross product is going to equal that cross product. So we end up with 3x plus 5. When I do 5 times x minus 7, we get 5x minus 35, and we have a linear equation now that we solve. So I'm going to subtract 3x, and then I'm going to add 35 to move the constants to the left. So we have 40 equals 2x, which means x equals 20. So that's one part of this. And then on the other side, we got u equals negative 7. So that's going to be 3x plus 5 over x minus 7 equals negative 7. And again, let's make that the fraction by putting it over 1. And then we can set these cross products equal to each other. So that's the green part's going to be 3x plus 5. The part in blue is negative 7x plus 49. Again, another linear equation. I'm going to move my x's to the left this time to get a positive coefficient there. X's go to the left, my constants go to the right, so I'm going to subtract 5. We have 10x equals 44. Divide both sides by 10 and reduce. Common factor here is 2. So we have 22 over 5. Now, in this original problem, we had a denominator of x minus 7. So my restricted value would have been 7. But I don't see that for either of my solutions. And provided that I've done everything correctly, these guys are both going to work out. Now I know this can seem like a lot going on there, and I get that. Well, let's just quickly review about what happened. This equation looked ugly. But we saw that we had the same variable expression. We had just the variable expression to the first power and that same variable expression squared. So by doing a u substitution, I'm able to rewrite it here in pink, and I have a nice quadratic that I can factor. U minus 5 times u plus 7. I solve that quadratic equation. I get u equals 5 and u equals negative 7. And from there, I make my transition from the u to my original expression x. And now I have two separate equations that I'm going to solve for x. Now they happen to be rational equations, happen to be proportions to be more precise. So we set the cross products equal, and then we solve those guys that are left over. Now, you could have expressions that are even more complicated than that. So if I had suppose I had the cube root of x plus 2 squared plus 2 times the cube root of x plus 2 minus 35 equals 0. You'll see that that's very similar to what we just did. You have the cube root, and then you have the cube root with double the power. So if you let u represent that cube root expression, then this becomes u squared plus 2u minus 35 equals 0, and you're going to proceed the same way. So, I guess while I'm here, let me just go ahead and do this. So u minus 5 times u plus 7, the same factorization we had above. U equals 5, whoops, or u equals negative 7. Now, in this case, when we make the substitution, it goes back to the cube root. So the cube root of x plus 2 equals 5, or the cube root of x plus 2 equals negative 7. So the same concept as what I had above. It's just a different expression that I'm substituting with the u. And at the end here, instead of having a rational equation or a proportion that I need to solve, I have a radical equation. So we would raise both sides to the third power here, and we'll do it over here as well. So we'd have x plus 2 equals 125, which means x equals 123. On the other half of this, x plus 2 equals negative 343, which means x equals negative 345. So 7 to the third is 343, so if it's a negative, it's a negative 343. But the idea behind each of these guys is exactly the same. All right. Well, hope all of you watching got something good out of this. If you know people that need help with math, or they're doing the same kind of stuff, please put them to my channel. Like, subscribe, ring the bell, all the fun stuff. Make sure you dab in 6-7 and all the cool stuff the kids are doing these days. Until then, I will be back tomorrow, and we'll be doing, I'm not sure. I think tomorrow is going to be inequalities. So the inequalities will include linear inequalities and quadratic and rational inequalities. So some good stuff there. Yeah. So until then, you guys have a good evening. Take care.